Bom dia. The rest is English, but there will be some surprises. So our agenda today would consist of two parts. The first part, I'm going to talk about authenticated encryption and some new features and pitfalls, and I'll connect this to the recent WPA2 attack that has just been released a few days ago. You will see how this is connected. And the second part would be, don't encrypt without authentication. I've been going around and saying these things, but people keep thinking that encryption is also safe when you have an adversary who can change the ciphertext. So the answer is no, and we will see this. All right, so agora não falarei muito e direto ao ponto. So first part would be authenticated encryption. I'll talk about the rise of AES-GCM. I'll give some historical account, and I'll talk about the brittleness, how dangerous this mode is if you ever repeat a nonce. Sounds familiar from the last few days of attacks. And I'll talk about how you can change the mode and propose a different mode that would be nonce misuse resistant, in a sense that you can repeat nonces and nothing would happen. And this is the AES GCM SIV. SIV is for synthetic IV, and its efficient instantiation. All right. So let's start. So first of all, it is very important to have an efficient authenticated encryption scheme. For example, the most prominent example is the client-server TLS communications. So every time you open your browser and you connect to a server, you hopefully are initiating a TLS session and with some authenticated encryption. And by now, AES-GCM, so ASD encryption, and GCM stands for Galois counter mode, is already the de facto mode of operation that is used everywhere for authenticated encryption. It is already today part of the current TLS version 1.2. It is planned to be one of the only two supported AEAD schemes in TLS 1.3 that is coming soon. So AEAD is the authenticated encryption with addition authenticated data. And it is the preferred server and client choice for leading servers and browsers. Especially for the clients, the server always prefers the AES-GCM because all servers already have hardware support for both the Galois counter mode and the AES by 2 instructions, and the clients, the 64-bit clients already have these instructions or similar instructions, so they would also choose as a first preference AES-GCM. The advantages of this mode, first of all, it started in 2006, around 2006, it came out with a security proof, and this was a novelty, and it has excellent performance on modern CPUs with AES instructions and carryless multiplication. This PCL mul QDQ, this is the instruction that speeds up polynomial multiplications. So let's see, how did it get so attractive? So if we go to 2009, up to 2009, the dominant ciphers were AES in CBC mode, RC4 and HMAC SHA-1. These were dominant. So 90% of the traffic was with one of these two combinations. And AES-GCM did not even exist in any practical sense. All right. So let me give you some account of performance. So RC4 for the cipher and HMAC SHA-1 for the authentication had performance of 2.5 cycles per byte. on a server CPU. So lower is better. AES and HMAC SHA-1 was approximately 23. And AES-GCM had approximately 22 cycles per byte. So of course, if you want to choose the best performing mode, you would go for RC4 and HMAC SHA-1. And this was the dominant mode, but there were starting to see problems with the security of this mode. So then the ecosystem moved to choose AES and HMAC SHA-1, and then there was some problem with the CBC mode, so back and forth. And AES-GCM really didn't show any performance advantage, right? So nobody would try to push the ecosystem to change the preferred cipher suite for no reason, for no performance reason. So this was the situation up until 2009, and then around 2009, Intel announced, and by 2010, there were already CPUs with these instructions. So AES and I, these were the instructions to encrypt faster with AES and a 64-bit polynomial multiplication. It is the carrierless multiplication, and this was built for many purposes, but one of them was to speed up the AES-GCM because it is built on polynomial multiplication. Not 64-bit polynomials, but 128-bit polynomials. But if you have this component, you can write a piece of software that would do a wide polynomial multiplication for you. On top of this, since 2009, there have been continuous software and algorithmic optimizations for implementing AES-GCM better and better. And also, after the architecture of these instructions were announced, then the microarchitectures have been improving. So the AES improved the latency and the throughput and also the carrierless multiplication. So with this process, I'll show you where we are today. So this is the 22 cycles per byte. This was before there were hardware instructions to speed up AES and GCM. So it's not even reaching the 22, just the 22 is up there, but that's the end of the graph. So in 2010, this was the first generation of processors with these instructions. So from 22, it dropped to 3, around 3 cycles per byte. So this was already a very good reason to start moving servers and clients to use AES-GCM. The next iteration was 2 years after the Sandy Bridge processor in 2012. It dropped a little bit to 2.75. What happened was that the throughput of the AES was improved, but still the authentication, the Galois counter mode computations were not sped up because the carrierless multiplication remained the same. So there was a modest improvement. And then we see a drop, a beautiful drop here, right? So what happened in 2013, the carrierless multiplication was also improved. So it's like two competing elements of the mode. So you improve AES, then the carrierless multiplication remains the tallest pole in the tent. And then you improve this. So in 2013, it was dropped already to 1 cycle per byte. The year after, the shrink, the Broadwell CPU, 0.76. And now, starting 2015 and on Skylake, and there are already newer CPUs, it dropped, the performance is 0.65 cycles per byte. So remember, we started the journey from 22. And here we are at 0.65. But what is so special about 0.65, this number? So the performance of only the counter mode, only the encryption, is also around 0.65 cycles per byte. So this processor in 2015 is the first generation where authentication and encryption is at the same cost of only the encryption. In other words, this is the top performance possible on these type of CPUs. You cannot ask for more. You cannot get less than the encryption if you're doing encryption and authentication. But now you are getting encryption and authentication for the same cost of only encryption. So this was the ultimate target. So now if you compare this and his, you see a big reason why move to AES GCM. And indeed, what happened? So I'll show some evolution. So in 2012, TLS 1.2 was announced, and this was the first time where AES GCM was officially part of the cipher suites that the server and clients could choose. But there was very slow proliferation. So only maybe 1.2% or 3% or something like this of the traffic really used TLS 1.2, right? So you have to use TLS 1.2 if you want to use the AES GCM. So this was proliferating very slowly. The majority of the TLS was 1.0, which was broken, and then there was a strong push to upgrade this to TLS 1.1. So most of the effort was invested towards the first update of the protocol. And I told you before, 90% of the traffic was with the good old, or maybe I should say bad old, AES-CBC or RC4 with HMAC SHA-1. Now let's see what happened. In 3 years, the instructions were introduced. There was already one generation, next generation of improvements. The AES GCM in December 2015, I was tracking this. So 55% of the traffic was AES GCM, 30% was AES CBC, and there was another one, Cha-Cha and Poly, which is a third cipher that emerged, and it was designed for the low-end CPUs, the 32-bit CPUs that do not have the hardware support for AES and for the GCM. So for these processors, this is a faster mode of operation. And 2016, we see this picture already. So 64% of the traffic is AES GCM, and AES CBC dropped to 20%. Remember, it was around 90%, and Cha-Cha Poly stabilized to 15%. More or less, this is the share of the low-end CPUs, the phones, let's say, more or less. So this is why it stabilizes on this value, and the trend is going on. So basically, we can see the evolution that most of the traffic has already, client-server traffic has already moved to the modern cipher authenticated encryption, and is enjoying performance and security. So, if it's so wonderful, why am I giving this talk here? You can sense that there is a but coming. So what happens if something goes wrong? So the AES GCM needs to have an IV, initialization vector, or we call it in the cryptographic language, a nonce. And the most important thing is to never repeat a nonce. So this is, if you want to use this mode securely, never reuse a nonce, of course, with the same key. So it sounds very simple. So what happens if you repeat the nonce by mistake? So the counter mode, the privacy part of the encryption is gone. And you lost these two messages that you encrypt it with the same nonce. But this is a small disaster. An even worse disaster is that the integrity is completely broken. It's not only these two messages, because if you repeated the nonce twice, then there is some computation that can be done offline. It will reveal the authentication key of the AES GCM. So from that point on, an adversary can forge any message, not just these two messages that were compromised because you repeated the nonce twice. So you lost the integrity. So you really should not repeat a nonce, and you ask yourself, if there is such a crisp warning, why would an IV repeat, right? So I will tell you. So let me give you a brief history of bad randomness. So first of all, it is very difficult to get real good randomness. And for this, for example, there is nowadays a new instruction by Intel, and it's also already in other processors too. By now, it's RDRAND and RDC. These are two instructions that can actually give you entropy from an entropy source that is built into the processor hardware. Okay? But until there was this instruction, it was very difficult to actually do this. But then there is the conspiracy theory. You have this wonderful instruction, but there were many who refused to use it. We cannot trust Intel. Maybe they planted a backdoor, and the entropy is not good. So although there was a good instruction, it was still not used by everything, and people, libraries still used the Linux dev random that is just collecting some randomness from the system. But this is not really pure entropy coming from a real physical entropy source. Well, eventually, by now, I think that the ecosystem has already agreed to this novel idea. If you have a source of entropy and you add it to this, there is no damage, right? So you enjoy both worlds. So today there is a collection of entropy from multiple sources, including the RDRAND. I'm just giving some history. So there was the famous bug in 2008, the Debian Linux in the RNG receding. So it turned out that many random generators were actually predictable. And in the 2010, the PlayStation 3, right, the private key was recovered because there was no new generated random source for each signature. So you can see that getting a random IV is not trivial. There are many mistakes that happen with this. Here is a nice story. It's a paper by Lenstra and other co-authors. In 2012, they collected 6.5 million RSA public keys. So everyone can harvest. It's just a matter of time and to write the crawler that would grab the public keys from many servers. And this is what they found, that 71,000 keys were used more than once by different servers, right? So if two servers have the same public key, it means that they also have the same private key, and it means that one can compromise the other and vice versa. And you ask yourself, how is it possible that somebody generated, let's say, a 2,000-bit key and got the same public key? Well, the answer is bad randomness. They didn't choose the primes correctly. Another interesting thing, so this is 71. So 71,000 were just, negligent generation of a private public key pair. And around 13,000 had a common factor, and this is also amazing. You take two public keys that are completely different from different servers, you compute the GCD, the greatest common denominator, and you get something that is greater than 1. Voila. So you have factorized both keys. So both of these servers are hacked with this. So this was a big deal to take so many million public keys and go over all the pairs. So they had a special technique to actually do this in feasible time, but that's a fact. So you think, again, how is it possible? I mean, how do you generate an RSA private key? You just get two random primes, right? Now, if your source of randomness or the way that you apply it or the way that you use it is not perfect, then you are most likely to have not really random primes. So not all of them. So if both primes are common, then you are here in the 71,000 cases, very bad cases. But this is a very bad case as well, right? So we can see actually that that getting random IVs and random keys and random seeds is a difficult task. And there are failures again and again. It is just interesting to say, I'll just show some computations. It is interesting to actually to look at these data. 6.4 million keys and 71,000 were compromised, plus 13,000, and do some computations of how much entropy is in this key, in the public key. So we did some computations, and it turned out that the average RSA key has only 32, 33 bits of entropy. This is the abstract conclusion from this experiment, right? Now, 32 bits of entropy is not very much, right? It can easily today be brute forced, and we will see later how easily you can brute force a 32-bit entropy source. So again, and now in May 2016, there was another paper by these gentlemen, non-disrespecting adversaries, practical forgery attacks on GCM in TLS, and this is from the abstract. We identified 184 HTTPS servers repeating nonces, okay? And I explained, the worst nightmare when you're doing ASGCM for privacy and authentication is that you repeated a nonce. So you lost the privacy of these two messages and the authentication of everything. So they just, so 184 cases were not really, were repeating nonsense, and also they discovered over 70,000 cases or HTTPS servers where there is a large risk of repeating the nonsense. So you see again and again, this problem of randomness is appearing. Failures with randomness appear again and again, and especially in the AES-GCM case, where the worst thing you can do is repeat a nonce. All right. So the conclusion is that randomness can repeat, and it does repeat. So what can we do? This is ASGCM. It is now used everywhere. There is dedicated hardware, instructions, and devices that have dedicated hardware to speed this up. Everyone is using this, and it is by far the best mode. If you use it correctly, it's the best mode compared to everything else. So can we find a scheme that would be resistant to nonce misuse? Nothing happens if you repeat a nonce. You want the same performance benefits of the ASGCM, so you want the security, you want the performance, you want it to be a small change compared to AES GCM, because all the libraries and so much hardware and devices and protocols are already using AES GCM, so there are highly tuned assembly routines that do implementations and Java codes and whatever. So if we can find something like this that would use the same building blocks, we can at least reuse components, so deployment would be easy and it would be very efficient. So can we find something that has security, performance, easily deployable, and very efficient with reuse? So wouldn't it be excellent if we can find something like this? So yes, there is something like this, and so we can have the cake and eat it. So this is what I'm going to explain, and I will just go and explain something about the SIV encryption. It is actually a general concept. SIV stands for synthetic IV. It is from a paper by Rogaway and Shrimpton. They had some proofs about this, and they are saying you have two keys. One of them is going to be the encryption key, and one of them is going to be the authentication key. And you have a message and a nonce. And the first step, you take some PRF, some pseudo-random function, whatever you want, that uses the first key. Okay, the first key is the authentication key. And you compute the result. Let's say that the result is T. And the second step, you encrypt the message M using the second key, the encryption key, and the nonce T as the nonce. And then you get the result. This is the ciphertext, and of course, decryption is the other way around. So the trick is actually that the nonce that you chose in the beginning is not the nonce that goes into the actual encryption, because what goes into the actual encryption is the result of the nonce and the message and the first key. So the IV, or the nonce that is used for the encryption, is synthetic in a sense. It's not the one that you chose for the encryption. It depends both on the nonce and the message. So if you repeat a nonce and you have a different message, then the IV that is going to be used for the encryption is going to be different. So only if you repeat both the nonce and the message, you'll get the same T, but okay, and the same encryption, but this is not a surprise, right? Because this mode of encryption and authentication is deterministic. Of course, if you use the same nonce and the same message, you'll get the same result. There is no security leak from that, except for the fact that the message is the same message. But this is inevitable. This is part of a deterministic mode. So the problem with that paper was that there was no efficient instantiation to actually do this. It was just something theoretical, and whatever was proposed was actually performing at the level of the CBC encryption, which we wanted to abandon, as you saw previously. So this is work that I've been doing in 2015 with Yehuda Lindell from Bar-Ilan University. We actually wrote a paper with, we called it nonce misuse resistant mode for less than a cycle per byte. So you can, and this was published in 2015, and in 2016 we teamed up with Adam Langley from Google, and we had an improved version, and it was submitted to the IETF as a proposal for a mode. This was already in 2016, beginning of 2016. Now we are in 2017. It has gone through several revisions, and I guess that it would become an RFC very soon. So in the next meeting or so. So it's underway. So what is this wonderful mode? So you can think about it For simplicity, it's like doing ASGCM, but in reversed order. So in ASGCM, you take the message, you take the nonce, you have the key, you first encrypt the message, and then you apply the authentication on the ciphertext. That's the definition. And then it means that if you repeated the nonce twice, you lost both authentication and integrity. But in ASGCM sieve, the synthetic IV, we just do this the other way around. We take the G hash, and this is the component, the hash function that goes over the message and the nonce, and we apply some universal hash function on this with some good properties. I'll skip this. So we have a value T that depends on the message and the nonce, and actually also on the AAD. And this is being used, or 96 bits out of this, or technically actually 95 bits out of it, because we want 1 bit to differentiate blocks for encryption and blocks for authentication. So 95 bits are used as a randomized synthetic IV for the counter mode, and then we just encrypt. So you can think about it, it has the same properties or the same underlying elements of ASGCM, but nothing happens if you misuse a nonce, if you use a nonce twice. Unless you are using the same message twice and the same nonce, and then, okay, somebody who's looking at this traffic would know, okay, you've done twice the same thing. That's all that leaks out. The important property is that the underlying elements are identical to the existing ASGCM. It means that we can take the same, we found some, you can take the same library, like OpenSSL library, and call the same primitives and get this, this encryption. Another element that was added to this is a derived key mode, and this is to extend the lifetime of a key, because this is now becoming yet another problem. You want to use, you want a server to have a key that would last for a long time. And with high volume encryptions nowadays and so much data, the keys are wearing out quite quickly. So for example, if you're using with ASGCM or with the GCM sieve, you're using a random nonce or a synthetically random nonce, and it has only 95 bits or 96 bits. It means that after 2 to the 48 times, you will repeat the nonce, and you're back in problems. You might say 2 to the 48 is not a problem, but it is a problem, especially as the specifications of NIST require that the probability of repeating a nonce in a randomized IV implementation should not be more than 2 to the minus 32. That's the requirement. So this means actually that you cannot use ASGCM and also GCM sieve. You cannot use it more than 2 to the 32 times. Okay, 2 to the 32 times are exhausted quite fast, right? You can imagine. We'll see later. I build up some tension for the 2 to the 32. So what we did in the ASGCM sieve, we also added a key derivation. So this is just a scheme that is saying the following. You have a nonce, you have added data, and you have a message. And instead of going and using the cryptographic scheme, GCM sieve or whatever, you first pass the nonce through a key derivation function, some pseudo-random function. And the pseudo-random function would spit out a key that would be used for that nonce. And then you continue as usual. So basically, you can apply to any encryption scheme. You just prepend a key derivation function before the encryption. Of course, you need to do the same for the decryption, right? And this extends the lifetime of the key. So just without getting to too many technical details, ASGCM sieve that uses this mode or this trick can encrypt up to 2 to the 64 messages. There is some restriction, they cannot be too long. You cannot encrypt 2 to the 64 messages. Each one of them is of length 2 to the 32 blocks. But nobody really wants to encrypt so much data. I mean, typical messages are much shorter. So for short messages, you can encrypt up to 2 to the 64. This is basically the limit of encryption in general with 128 bits block, and this is what we use for AES. So, bottom line, okay, so this is the comparison. Oh, there is some line here that doesn't show on that. So this is the GCM sieve, the encryption and the decryption, and you have on 3 CPUs, but what we are interested nowadays in 2017 is the Skylake and processors and further, where AES-GCM is at 0.65, and as I told you, this is where you get authenticated encryption at the same performance cost of only the encryption. So you cannot get better than that. And we can see that the encryption is 0.94, so the promise was less than a cycle per byte. And magically, decryption is also 0.65. So for decryption, you can decrypt at the same cost of decryption and check the authentication. The surprising reason why there is a difference between encryption and decryption is the mode itself. Because when you are encrypting, theoretically, you cannot do better than first pass over the whole message and compute the hash function, and then start to encrypt. So there is built-in serialization in the mode itself. Whereas when you are decrypting, you can interleave these operations and do the same trick as in AES GCM. So this is the reason why encryption and decryption are different. So in summary, a non-misuse resistant authenticated encryption at extremely low cost, almost as the AES GCM, this is something of value because we saw that there are again and again problems with generating entropy and with making sure that IVs don't repeat, and we have a proof of security. It's easily deployable because you can just use the same libraries, and it is already, okay, here it's soon to be integrated, but Google is already using this mode in Boring SSL. This is their own version of OpenSSL, and they are using this this mode, and they're already using it for a certain application today. So this concludes the first part, and the second part is the part where we are going to see how easy it is to brute force 2 to the 32 bit entropy. Let me just see how much time I have. How much time do I have? How much time do I still have for this? All right, well, keep going until you you throw stones at me. All right, so, okay, part 2 is don't encrypt without authentication. For the audience, I even wrote this in Portuguese, so that if you remember anything from this, is don't do this. And we keep seeing technologies that come up with encryption. So I'll just give you a brief account, a historical account of some progress in this. So this is work that I've been doing for some years already with Rodrigo. He's there, well, I guess. because he's going to explain. There is a video, and I wanted him to explain the video in Portuguese. Uh, we call it the blinded random corruption attacks. So what we were demonstrating is that if you have memory, or let's take memory. This was the attack, and the memory is encrypted, but there is no authentication. And you are the attacker, so you can read and write the memory. That's you can read if you can read it, you can also write it. And the reason why it was encrypted to begin with was the assumption that there is an attacker who can read the memory, and we want to prevent, to protect the privacy. So, although the attacker cannot decrypt the ciphertext that he is reading, he can still make modifications. And the modifications would cause something to change in some unpredictable way. And there is a belief, a naive belief, that since this is so unpredictable and so much not controlled by the adversary, that maybe this is good enough. So we already know that this is not good enough. If you were here last year, we made a demonstration that showed that we can log into a locked system with overriding the memory. And I'll just remind this type of attack and the principle it was based on. And there was also another paper that I published with a different team, that we actually injected fault attacks. Okay, this is a fault attack. You change something in the memory. If you just do it in the right place and you attack the right code, and the code was really negligent enough not to check, then you can make the fault attack on RSA, and we were actually able to grab out encryption, the private key of RSA from an implementation, from some library. So, okay, I will skip this. I just want to go and okay, I explained this. I just want to show how this was able to, how we can be a root on a locked system with a blinded random block corruption attack. So if everything is encrypted with a block cipher and you modify a single bit somewhere, it is going to corrupt a whole block of 128 bits with something that is unpredictable. But we looked at the way that the login program of Linux was working, and actually, if you look at this, there is some pre-authentication flag that if it is set, it would not ask you for the password anymore, because this is built for cases where you already authenticated yourself and you just want to repeat something. So that's the way it really works. So what we see, that if we can just go over this pre-authenticated flag, or the region in memory where this pre-authentication flag resides in memory, and we can just hit it randomly, we are, with probability of 50%, all right, going to be able to flip it to yes, all right? So within one or two such experiments, we will be able to log in to a machine without having the password. So you're saying, okay, who cares? We have a machine, it is locked, and you can, maybe it's a machine, maybe it's like a small phone, it's soldered, and so forth and so forth. But the actual threat, if we want to look at this, is the cloud situation. The cloud situation where you have a hypervisor, and the hypervisor controls the VMs of the users, and the hypervisor can enter a VM into a debug mode. That's a privilege of the hypervisor. So even with the technology that has been recently proposed by AMD, they were saying, we're going to encrypt the whole memory. You can still do the same thing because the hypervisor can put the victim VM into a debug mode, and the same login program is running in the background. The user doesn't log in with this. The user would typically log in with an SSH application, but the login program is running in the background. So the hypervisor that can identify where in memory these precious variables are residing can enter a debug mode and can write something. So again, the hypervisor can read the memory, but since every VM with this technology is going to be encrypted with a different key, it is not going to be useful because the hypervisor would read with its own key. So there would be a decryption with the hypervisor key of something that was encrypted with a different key of the VM, of the guest VM. So it's not going to help. The hypervisor is going to see garbage, and this is the promise of this technology. But the hypervisor can overwrite, and if the same login program is running in the background, well, the hypervisor can log in as root into the guest VM, and then if the hypervisor is root, it can just copy everything. It doesn't need to go through memory. So all of the memory, the encryption of the memory is not useful anymore. So again, as we see, this is the result of encryption with no authentication. So the old video. I'm going to call Rodrigo. We are going to show two videos. So one is the previous attack and the new attack, and we're going to show the videos, and first I'm just going to show the new. So what is new? We call it a single bit flip, right? We were able to attack a conditional that happens to be a critical and just flip from 0 to 1, actually, something from 0 to 1, and this happens with very high probability. So after 1, 2, 3 attempts, you'll get what you want. So in a sense, one could say that although these are frequent and we were able to demonstrate, it's a weak attack in a sense, because it can only be applied to a conditional bit that happens to be critical. Okay, so guess what? I have this. Now watch this. But we will show the video later. So what we are going to show right now is actually that there are ways to do more, not only on a single conditional bit. So here you can see memory, and we just look at the memory addresses and we count 128-bit blocks because that's the standard encryption, and we just view it this way. And so just imagine that everything that goes out to memory is encrypted, and when it goes back it is decrypted, but every VM has its own different key. So what happens is that we can look here, we can see many variables. So we can take 3 examples. A variable that is an unsigned character, so it's a byte, it's an 8-bit. So another variable is 16 bits, and another type of variable is an unsigned integer, a 32-bit, right? So you can guess where I'm getting it. Instead of just looking at the possibility of flipping a single critical bit, we can allow ourselves to go further. So to find some place where we can brute force a block, that we will just change a value of an integer, a 32-bit integer, to something that we want with many attempts, and assuming that the rest of the bits will not affect the rest of the computations. And if we can identify something like this, then we are able to attack much more than a single bit. So just here, so this is just, and now there will be this, the famous, so it sounds, okay, unbelievable, right? But if you look at the way that the Linux kernel is built, so we see that the structure of task has different IDs, and guess what? The effective UID, right, is a 32-bit value. So wouldn't it be wonderful if we could take the effective UID of a guest VM and change it to the hypervisor's ID, right? So in that case, you can just escalate the privilege of the process. And okay, so okay, I'll just skip here. So did we find a winner candidate? So yes, and we'll now show that it works. So you have many data elements with different sizes. Yes, this is in the kernel. Can we find something that we can fully brute force, something that is a 32-bit integer? How long do you think it takes you to just do 2 to the 32 attempts until you succeed? Not too long. We will see it right now. So yes, the effective UID, and you can, if the successful attack would elevate the privileges, and what happens if other variables are changed? Okay, we don't care, and is it going to succeed? So I will just, okay, I'll skip the limitations, and now I'll ask Rodrigo to show the wonderful video with this attack on 32 bits, and he would explain this in Portuguese, so it would be easier to follow. All right, where is the... It is running in the background, I think, one of these. Yes, okay. So we'll show this. Huh. Okay.
Okay, so let me try to explain what we actually doing here. So we have two VMs. One of the VMs is the attacker VM. The other VM is the victim VM. What we want is, in the victim, we have a process that will be running. That process has no privileges. It's just a normal user. The way that we show it, we show the output of the ID commands to show that the user has no privileges, and we try to read a secret, and basically we don't manage to do it. Then in the attacker, what we do is like we connect to this debug mode for the VM, and we start brute forcing. You see that in the output, it will show a new value for the effective user ID every like 10 seconds. Actually, that's millions of tries, okay, like in those 10 seconds, but we only print every 10 seconds. And you see that at some point, that process will hit 0, which is the value for the effective user ID of the administrator in Linux. And then basically it stops brute forcing and just like keeps the privilege. So the cool thing here is like it's just one process that we need on the victim, but that process has no privileges. You will see that in the very beginning, what this process does, besides being like wanting to be elevated, is actually spawning multiple processes. And the idea to do that is so we can locate where in memory is our victim, right? Because the memory is encrypted. As an attacker, we know that we could brute force some bits, but we don't know where they are. So what we do is like this process is spawn multiple processes that basically forces the memory allocator in Linux to be in a certain behavior. Then we start killing processes and creating new ones. So finally, we created a gap in the memory allocation. We know these child processes are adjacent in memory. So we know that when we're hitting our process. That's why even when we fail, we actually just give the wrong privilege to the software. So you will see when the program is running and printing, it will start printing many different user IDs. And it only stops when it actually succeeds and gets 0. He wanted me to say that in Portuguese. Well, but there is some English speakers in the audience. So it is running. As you can see, this is the victim. So the process just wants to be elevated. Ouch. It's going to be very hard to see. It's very hard to see, right? Yeah. Well, it's going to be hard to see. I'm sorry. Oops. Oh, okay. A little bit better. So I will share the video later as well, okay? So essentially here I just run the command. I will basically read what is going on the video then. So here I just run the command ID. So it shows that our user is BS Demon with like the user ID is 1001, right? So that's what we want to basically to somehow change, right? So when this user tries to read a secret, it's just a file in the etc directory, and it has no permissions, even though nobody's seeing, believe me. So, or if you want, you can come closer to the screen, okay? I'm sorry for that. So the user don't have enough permissions. So it's basically doing like I just listed the directories, so you see that this process that we're executing is not suite root or anything. It's just a user process, something that the user can just run on the machine. When you run it, the very first thing that happens is all these forks that I mentioned. So the process starts creating a lot of childs to basically make the memory in a certain way, and for us to be able to identify where it is, even in the encrypted memory. As you can see, each of these child process is still keep the same effective user ID, which is the original user, so 1001. So when the brute force starts, so you see, like I change the terminals, so I start doing the brute force. So when the brute force starts, essentially what happens is like, you see the original effective user ID is 1001. So after some seconds, we print again, right? Just like to see what is the new value. But now it is like, it's showing like a big integer, okay? We're printing as signed integer, so it's showing negative, but it's an unsigned value actually, so it's a big integer. Then again, another one, and it's all random values. You see, like our process is becoming users that don't even exist on that machine. But in the way that this system works, if that process don't try to do anything that requires privileges, it's all fine. The system keeps running, right? There is no crash, there is no nothing. We're brute forcing a data structure in the kernel, and we're actually putting random values in that data structure, and the system continues running as if nothing's happened. And then, like you see, like now it's getting like more values, and again, millions of tries are going on the background. We're printing just every like 10 seconds or so. And the matter is, it's a 32 bits. It's random values. Each of the bits are random independently because it's through random property that encryption gives to you. So in a 32 bits, at some point, it will reach 0. That's what we want. When it reaches 0, the process tells the brute forcer to stop. And essentially, it just keeps with that privilege that it's just gained. It's going.
Did we get there? It's going to. We'll see. Eventually, you will see that we end up with root, right? So now while we are waiting, when this hits, we'll see. Yeah, okay. That's it. Hello, root. So again, what is the the lesson taken. All right, so now we can get back to the presentation.
So you see, like, once it got UID 0, which is root, the process just called a shell, because now that shell is root, and now you can basically read secrets, you can do whatever you want in that machine, right? It's a simple brute force. The fact that the memory is encrypted made very little difference.
Yeah. All right, so what we saw actually is an upgrade of the same type of attack over encrypted memory. We don't know what the values that we are reading are. We don't know how they are going to be changed by some change in the encrypted memory, but yet we can identify places, like in the first time it was a single bit, where a single bit was critical to flip from pre-authenticated or not pre-authenticated, and allowed the program to get a login as root. And this time it's more. It's not so this type of attack on encrypted memory is not only on a single bit. You can apply this to other things, and you can just imagine that this process ends after 2 to the 32 attempts on average. Of course, the sequence here was only showing after 10 seconds, but this is absolutely doable. And in reality, we see many short variables like 32 bits, and if we find smaller, it's even better. And right, so again, don't try to encrypt without authentication unless you are absolutely sure that the attacker cannot overwrite your memory or your ciphertext, but this is very difficult to promise something like this, because to begin with, you encrypted your memory because there is some adversary who can read that memory. So in most cases, you can think of, if an adversary can read the memory, there is no reason why he could not also overwrite the memory. And this means that you really need some means of authentication, even if it is not a foolproof cryptographic authentication, even something that would fail the system and would frustrate an attacker. Just imagine that somebody wants to do this hack over 32 bits, and there is some kind of authentication that gives you another 32 bits of authentication, or even 16 bits of authentication, something very simple. Now something that took a few minutes is going to take a very long time. So I would say, okay, that's it. And thank you for your time. And I'm done with this. Thank you.